Oh, tēnā katoa. A very, very warm welcome to you all, joining us from near and far and from pretty much every level of our community today, from central and local government, from industry bodies and from people on the ground working on farm around the motu, and also from civil society. We've got lots of people joining us from rural support trusts and various sustainability organisations as well. So we're really, really grateful that you've been able to join us today. We'll get started slowly to give everyone a chance to keep joining us. We're expecting 300 people in our Zoom room today, and we're currently at 121 and rising steadily. So we'll just have a gentle, slow start to the morning. But just to begin, ko Alexandra Keeble tōku ingoa. I work in communications for the Deep South Challenge, Changing with Our Climate. And this is Angela Halliday, who's one of our partnerships directors and who's been instrumental along with our sister challenges in organising this Rolling Symposium today. So there's many special things about today and today's webinar. This is the first cross-national science challenge symposium. It's also the first rolling symposium, a term we've just coined ourselves, and it's jointly organised by the Resilience to Nature's Challenges National Science Challenge, our Land and Water and Deep South Challenge, Changing with Our Climate. We're also pleased to be working quite closely with MPI as well today to shape not only the 3 background webinars, but also the final symposium event that's coming up at the end of May. So we've never done a rolling symposium. While we're old hands at webinars, all of us in the 3 challenges, we've not hosted something quite as ambitious and with so many arms and minds as this event. So please bear with us if we have technical problems or if we don't get to you, if you have a question that we don't get to you with. But we're hoping that over the course of May, we'll be able to build a really solid conversation around the issues that come up over the course of this symposium. So we also haven't held a series of events that synthesize research from many different organisations that sort of coalesce around a single theme. So we've chosen the theme of drought, which obviously has reaches into all of our science challenges. There are climate issues related to drought. There's rural communities and also environmental issues related to drought, and obviously there's a huge number of land and water management issues that sort of fold into the question of drought. So we thought instead of working in silos, we'd work quite hard to try and break down the silo and bring you the best of our research, speaking to each other as well as to the wider community. So we have 3 webinars. I'm hoping that all of you, if you figured out that we have this webinar, you will also have figured out that there are 2 more webinars and a final full day event that we're holding at Te Papa on May 31, which is a Monday. That event is also going to be in person and online, but both of those categories are capped with attendance because we're trying to cultivate some interaction even for our online community. So we really encourage you to register as soon as possible for that online event if you'd like to come. And as I said, we have a packed Zoom room today. Yep, our numbers have risen steadily. And we're not going to be able to answer all questions, but our plan today is to have presentations from 3 very important climate researchers. We have Andrew Tait, Chief Scientist at NIWA, who's going to be talking through some of the supporting drought modelling that was done. I mean, NIWA does it in the course of its work, but was also done for an earlier Deep South Challenge project looking at the question of drought and future drinking water. And then we'll have Luke Harrington and Suzanne Rosier, Suzanne from NIWA and Luke from Victoria University of Wellington, looking at extreme weather modelling and the differences and challenges of extreme weather modelling, including drought, and looking at the financial impacts of drought that might be attributable to climate change. So we're really grateful to our 3 speakers for making themselves available today and for beginning this series of background research webinars, so that when we all come together on Monday, the 31st of May, we have some common language to begin a more complex, more nuanced discussion face to face. So a little bit of housekeeping quickly. Andrew will speak for around 15 to 20 minutes. Suzanne and Luke for around 15 to 20 minutes, leaving us with 15 minutes for questions. Please, even though we've asked you to introduce yourselves using the chat panel, which is beautiful, and that's a way that you can communicate with each other, please don't ask your questions in the chat panel. If you move your mouse around, you'll notice that there's a Q&A dialogue box. If you can use the Q&A box to type your question, please, and then we can moderate them from here. It's just a little bit difficult to invite you to speak and then manage so many people. So if you ask a question in the chat panel, it's unlikely we'll see it. Please use the Q&A panel. We'll also finally be making videos of all 3 seminars available in the days after each webinar, and they'll be available on our Deep South Challenge website, and I imagine on all 3 challenge websites. So to find out more about what's going on, you can visit any one of our websites and reach out to us via email or chat or any one of our social media platforms. So without further ado, I'll hand over to Andrew Tait and invite Andrew to unmute yourself, and then when you're ready, Andrew, to share your screen.
Thanks very much, Alex, and kia ora tātou. Share my screen. So, Kate, just let me know if that's sharing fine.
Yep, we can see you.
Lovely. Okay, so today I'm going to give you a little bit of a outline of some of the work that we've been doing on climate change and drought. In fact, on drought research in general. Very quick overview first of climate change projections for New Zealand and the work that we've been doing on updating those projections. Then a slide on the previous climate change projections of drought, which was work that was funded by MPI in a Sustainable Land Management and Climate Change project back in 2011. And then I'll finish off with some slides on the new climate change projections of drought, which Alex mentioned were part of a report that was funded by the Deep South National Science Challenge in 2020. So very quickly, just a bit of an overview of where we're at with our understanding of climate change projections for New Zealand. These slides are showing changes in the mean annual temperature projected between now and, on the far left, 2040, so about a 50-year time frame from 1990s to 2040. And you can see this is for an RCP 8.5. RCPs are representative concentration pathways. These are the emissions and concentrations scenarios that are run through the climate models. And RCP 8.5 is a particularly high concentration pathway. There are other pathways that we also look at in terms of low and middle pathways as well. But you can see from the left-hand side there, if we do assume that we'll go on a relatively high concentrations pathway, that New Zealand will be on average around about 1 degree or so warmer than we currently are. So given the fact that we've already warmed by 1 degree since pre-industrial times, then that's hitting our 2 degree warmer than pre-industrial already by the middle of the century if we follow that pathway. So that's quite interesting and useful information already to have in your pocket. The next 2 slides are looking at the end of the century by 2090. So these are more much more longer term projections. But the significance here is that the middle picture shows you the temperature change from between now and end of the century under a mid-range emissions and concentration pathway. And you can see that the picture there is still around about that 1 to 1.5 degrees Celsius warmer. So very similar picture to the mid-century projection on the left under the high emissions scenario. Whereas the far right picture for the end of the century is continuing on the high emissions pathway. We'll get to temperatures, projected temperatures in the order of 3 to 3.5 degrees Celsius. So what those two other maps there, the middle and the far right map, show is that by the end of the century, the emissions and concentration pathway that we follow as a globe, as a world, really does make a significant difference on the amount of temperature change we'll have by the end of the century. So hence the reason why there's so much importance on reducing our emissions. The picture for rainfall is more complex, and that's not surprising. New Zealand is quite a complex topography, and our rainfall regime matches that in terms of its complexity. But what we see here is essentially in terms of the annual rainfall change between now and the end of the century on the far left. There's a consistent message there, which has been consistent for quite some time now, even on previous iterations of the modeling work that we've done, of generally changes of more precipitation in areas in the west and drier in the east, particularly in the latest iteration of projections, the North Island, East Coast, and north of the North Island being the projected drier climates and the annual rainfall. The signal is very strongly coming from the winter season. You can see there in the middle, that's the changes that we're expecting for the winter. And that's where we have the most confidence in the models, because practically all the models that we look at are showing the same sort of pattern. And the intensity there of the changes is amplified in the winter season. So that's really influencing the annual pattern. So the takeaway message there from the middle and the left picture is that those wetter in the west and drier in the east storyline is really significantly dominated by the winter pattern. Not only will the amounts of rainfall change, but we'll also have change in the days with rain. And this is when you can start to tie into the rainfall picture, what we expect to see in terms of changes in drought. Because pretty much the entire country, except for places like west coast of the South Island and even into the southern and eastern parts of the South Island, the number of days of rain will also there'll be fewer days with rain. So that means that the number of days, dry days, increases throughout the country. So generally more dry days are projected. And that does tie in with what we expect with drought. I just wanted to very, very quickly point you to an online resource that has all of those maps on it. If you don't know, it's called Our Future Climate New Zealand, ofcnz.niwa.co.nz, and you can use that online resource to browse through various climate maps and download them for yourselves. Moving on to specific work that we've done on looking at drought. This is work that was done back in 2011, funded through MPI's SLIMAC fund. And it was based on the previous iteration of global models. But basically, that picture was the takeaway message there, and really was showing that areas that are currently susceptible to drought are likely to be even more so in the future. And the text there in the box was the sort of takeaway message there. So this was even for a mid-range emission scenario. So we had areas in the eastern regions of the South Island, especially Canterbury and Eastern South, and can expect to spend around 10% more time in drought by the middle of this century. So that was kind of the takeaway message from that 2011 report. And what's driving the changes in drought is not only the changes in rainfall, but predominantly the change in evapotranspiration, which is temperature driven. So you can even have areas where the change in rainfall might be increasing, but because of the warmer temperatures and the greater evapotranspiration as a result, you can still have an increase in drought in those areas. Moving on to more current research now, many of you will know that we spent some time recently over the last few years developing what we call the New Zealand Drought Index, NZDI. And we now have a web page there that is, the URL is there, which is called our New Zealand Drought Monitor. Now this is a web page that has current status of drought conditions based on this new index for all of New Zealand in a map form, for example, on the left, and that's taken from a few days ago. And as well as for different districts around the country, time series of the drought indicator going back over about 10 years or so. So this is a really important and useful resource that's been developed a couple of years ago and is quite actively used now for understanding where we are now and how drought conditions have been developing over the current season and how that compares with recent years. Now, based on that drought index, we've done some work with the Deep South National Science Challenge last year and using the latest suite of global climate models and downscaled to New Zealand conditions to look at the changes in drought based on that new drought index. And I'm just going to give you a couple of snapshot results from that report, but it would be interesting reading, I'm sure, to all of people joining in to grab a copy of that report. And I'll leave it over to the Deep South folks to put the link to that report perhaps in the chat. It's on the Deep South webpage. So just a very quick snapshot summary of the changes there. This is, for example, for summer, and the left shows the mid-century change in that index, and the right shows the end-century change, and just for that high emissions pathway, RCP 8.5. The takeaway message here is that almost the entire country, again, except those areas like in the coastal South Island, is having an exacerbation in drought conditions based on this new climate modeling work in summer in particular. And that, as I said before, is really being driven by the warmer temperatures in the summer driving evapotranspiration. But interestingly, we've done this seasonally now. When you look at winter with that very dominant rainfall pattern of increased rainfall, particularly in the west and south of the South Island, other than there, you still see an increase in drought in this NZDI intensity for much of the North Island and even for parts of the northeast of the South Island. So even in winter, we're looking at projected increases in drought intensity based on this new index. That, recall, is for the high emissions pathway, both for middle and end century. Now, one of the most interesting parts of this new report, and I must also say that the report was tailored to that particular project which was looking at drinking water, but there's some really good background reading material in the report as well. And one of the things I found most fascinating about the report that was authored by my colleague Abba Sood and the late Brett Mullen was this change in the seasonality of the New Zealand Drought Index. And I'll just step you through this, a couple of pictures here. The first slide here is for the far north location. The black line on those plots shows the current seasonal average NZDI drought index plot, and you can see that it builds up in the summer and peaks around February and then starts to decline again and as we go into the autumn. The other colors on that plot, the lines on that plot represent different emission scenarios, and I've got them noted down the bottom, so blue through to red. And that represents the change in that average drought seasonal profile for mid-century and end-century for this particular far north location. And even in the mid-century 2040 plot, you can start to see that not only does the peak of the drought intensity increase, even now getting into that the yellow shading, which is based on the NZDI index, what we classify as dry. But the plot is also starting to increase earlier in the year. So the length of the season in particular is changing, as well as the peak amount. And you really see that exacerbated in the right-hand plot by the end of the century, where the drought season, if you like, is now projected to be much more a spring-summer type of normal, as well as being more intense when it peaks under these projected changes. And I think that is something that will have significant implications for how we farm, for example, in New Zealand. That's a far north location. There's also several locations that are chosen in the report. I just picked another one here, being the central Canterbury, and you can see the same sort of pattern here. The climatology, the black line, is a little higher when it peaks in Canterbury than it is in the far north, but the pattern of change is similar, where you see an intensification of at the peak, but also an earlier start to the increase in the drought index, really meaning that this length of the season, if you like, of drought conditions is going far more into the spring than it is currently. So that's some interesting topic of conversation, I'm sure, for the rest of these webinars. I just wanted to finally show you another interesting picture, and this is work again based that we've been doing over the recent years. It's not the NZ Drought Index, but it's a component element of the New Zealand Drought Index. This is potential evapotranspiration deficit. We've been using PED as an drought indicator for many years now. This is a plot going all the way back to the 1940s, actually, showing the annual PED accumulation for the whole country. And I've just, and it's the last bar there on the right is only 10 months worth of accumulation, because it goes from July through to June. So we haven't got May and June on there yet. But I can, oh, sorry, go down. I can put a line across there at about 300 millimeters of PED, potential evapotranspiration deficit accumulation. And 300 is a rough number, a rough indicator of when a particular year was what we would call quite a droughty year for the country. And you can go back over time and look at how many incidents you have of crossing over that threshold. And you can see certainly we've had times in the past where this has happened. Decades like the 1980s, where we didn't have a particular year cross that threshold. But the recent decade in the 2010s is now, crossed that threshold 4 times, and this last year, we're 2 months to go. We're we're nudging up against it again. So there is an indication there from this plot, even just by eye, of seeing an increase in the sort of droughty years that we're already getting in New Zealand. But what I find interesting is to take this plot and then think about these climate change projections. And this is a projection just for that PED, potential evapotranspiration deficit variable. Based on just between now and the middle of the century, and only on the mid-range RCP 4.5. And you can see everywhere it gets droughtier based on this particular index, as we've seen in the NZDI maps. And if you just look at, on average, the sort of browny color around about 100 is not a bad ballpark figure for a kind of a New Zealand-wide increase in PED. And we could simply then take that historic data and add 100 millimeters onto the last decade's worth of data. And now you can see that 9 of the 10 years in this last decade exceed that 300 millimeters. So basically what we're moving towards quite short fashion, this is out to the 2040s, is a profile like what we're seeing there on the right-hand side with the red bars added to it. Really quite a different type of annual drought incidence and intensity pattern than what we've been used to over the last several decades. I think that's a nice, interesting and useful way to contextualize where these drought projections are going to take us. So look, I want to thank you very much for your attention today, and this has been a breezy, quick run through of some of the work that NIWA's been doing, and we really appreciate, of course, all the support that we get from our funders like MPI and the Deep South Challenge. Kia ora koutou, thank you very much.
Kia ora, Andrew. Well, thank you very, very much for that sort of whistle-stop tour through NIWA's work in this space. I do want to just pick up on something that you said and acknowledge your colleague, Abba Sid, and also the late Brett Mullen, but particularly Abba on her work on both the New Zealand Drought Index projections that you spoke about already, and Abba's previous work on downscaling and bias correction of global models to produce climate projections at regional scales that are hopefully useful to people on the ground. So thank you, Abba. I can't see if you're online, but I hope you are. I'd also just like to note for everyone asking questions, thank you very much for beginning to use the question and answer panel. Because we're not going to do questions until the end, please indicate who your question is for. You know, this question is for Andrew, etc. And we won't have the opportunity to answer everyone's questions, but at the end of the entire Rolling Symposium, if the questions that weren't answered, we will get answered and then circulate to everybody in text at the very end of the event. So for now, I'd like to hand over to Luke and ask Luke of Victoria University of Wellington to introduce yourself a little bit, Luke, and then to share your slides, share your screen when you're ready. Thank you.
Cool. Hi everyone, my name is Luke Harrington. I'm a Senior Research Fellow at the New Zealand Climate Change Research Institute, which is based at Vic. I'm just going to dive into this. Does that look okay from your end? Cool. Okay, so 15 minutes, let's see how I go. So this is a bunch of work, primarily coming back from a paper that we published 5 years ago now, in 2016. It's still kind of the most up-to-date version of the sort of types of work that we've been looking at. So we look specifically at individual drought events and figure out how climate change is affecting the likelihood and intensity of them. Why do we think drought is going to be getting worse with climate change? In actual fact, in a lot of parts of the world, the signal of low rainfall hydrological extremes isn't actually changing that much. That might be a surprising thing to hear. In actual fact, New Zealand, weirdly, we're not often this in a global context. We're looking to be in one of the hotspots globally of these changes. This is a recent paper that came out a couple of months ago from people in America, and they normally just focus on America or Europe or something, but they actually dug in and looked specifically at our area. So this is changes in mean sea level pressure over the last 60 years using climate models. And basically what you're seeing here is a southward shift of the westerly jet in the summertime that is really, really robust. It's a big pattern that you see right across the southern hemisphere. And it's well simulated, and we know the reasons why this is happening. It's a combination of two things. One is ozone depletion over Antarctica, and two is rising greenhouse gases. It shifts the tilt of how much air is in the tropics versus the poles, and it shifts the storm track southwards. And, as a result, more often over the summertime, you're seeing higher pressure systems park up over the New Zealand region. And really interestingly, from the same paper, they actually looked at what do you see over this area if you don't include these human influences on the climate over the last century, and it's a flat line. None of this red crops up. It actually goes completely dissipates away. So this is actually a human-driven signal. What am I going to be looking at? So we looked at the 2012-13 drought, which was the worst drought on record. And what are we going to do? We looked at how much more likely or intense was that event, seeing it in today's climate versus a climate of the late 1800s. So considering the role of all of the stuff that we've chucked up into the atmosphere between those 2 points in time, this is what we call extreme event attribution. So we're attributing the specific role of climate change on an individual event. There are some nuances to doing this sort of work. What we have to do is we have to look at the features of the drought that made it so extreme and actually cause those impacts. We have to focus on what were the meteorological drivers that actually caused the drought to be so impactful. But we also have to do it in such a way that we are confident that the climate models that we're using can actually simulate those types of things well. If you go into too fine a detail and really, really specific at one specific grid point, one specific location, the climate models are rubbish. I'm happy to say that. But if you look at the larger scale changes, the larger scale patterns of change, and we understand the processes which are driving them, we're actually really, really confident in what the climate models are doing, and they're doing it the right way. So for New Zealand drought, and for the types of climate models that we had available, this means sticking to large scale, like over the wider New Zealand region, high pressure systems, blocking highs, as we sometimes call them, and also looking at summertime average rainfall accumulation. So how much rain fell over the summertime. Just a note here that from this point on, I'm going to talk about summer as January through March, because that was the point with which the 2013 event was most intense. So bunch of figures here, they all look kind of overwhelming. The key point is that these are 3 different ways of looking at how intense the 2013 event was. And basically you can look at it from 3 different angles, and all of them say 2013 was bad. This big red blob here is the mean sea level pressure. So your high pressure systems from the weather maps, how anomalously severe was it over the entire summer. This middle one is basically looking at soil moisture anomalies. So low numbers means pretty dry soil moisture. And the red dot here was 2013. The reason why there's no subsequent data is because this was from an older paper. And the red here is basically showing where was soil moisture deficits at the end of the summer, the worst on record at the time of 2013. So this does not consider subsequent years. And you can see there's really, really widespread a number of places where it was the worst drought on record. That's why we're looking at 2013. We also know it cost the economy roughly about $1.5 billion at a guess. Sorry, not at a guess, Treasury estimates. Okay, so how did we, our team, look at understanding what was the role of climate change in this event? A couple of ways. First was looking at this big old blob of red, this anomalously high mean sea level pressure anomaly, and basically saying, okay, well, how often did we see these really severe anomalies in today's climate and the climate models running around 2013 versus in the late 1800s? And this, the x-axis here is basically showing that. This is for all years. The black is in the late 1800s and the red is for the centered around 2013. And then the other thing we looked at is it was really, really dry over this blue box. So this is just summertime rainfall accumulations. And 2 quick things you can see here. There was roughly a doubling in the chances of basically the really, really high tails of these 2 distributions here. So you can see the shift in the red bell curve. That means the likelihood of seeing really, really high anomalies or really, really high season average MSLP values increase roughly by a factor of 2. And you actually see, if you look at the very tails of the precipitation distribution, a pretty similar number, roughly a doubling in the likelihood. What you'll notice here is that actually isn't anything to do with some signal in the shift in the mean of the distribution, but in actual fact, there's increasing variability in today's climate relative to the past. And so what that means is you're increasing the likelihood of seeing extreme tails. So you're actually also seeing a likelihood of seeing wetter, very wetter than average summers, while at the same time seeing an increase in the likelihood of seeing very much drier than average summers. That's quite a sort of important point to recognize, that sometimes the mean signal doesn't always pull out really clear answers when there might actually be clear answers in the extremes of the distribution. So that's one way. Here is another way. We really wanted to look at the details of the 2013 event. So we ran some analysis to figure out what types of weather patterns. So this is, again, this is your high pressure system. This is your mean sea level pressures, things that you see on the weather maps, on the nightly news. We looked summertime, New Zealand only, and we did a whole bunch of analysis to figure out what are 12 common sort of weather systems that you see over the summertime. This is what we got. Red is high pressure, blue isn't. The numbers in each of these corners is how many days you saw this setup happen during the 2013 event. And we did a bunch of analysis and we found that these two numbers here, 12 days here, 20 days here, this was the driver of the 2013 event. It was this, these were the most anomalous numbers, most record-breaking numbers. And this is actually what caused the 2013 event to be so severe. There was too many of these looking days. So what we said was, okay, let's look at all of these model runs that we have of the current climate and all the model runs of the past climate. And we're going to count how many days are we seeing these things crop up in the summertime, and look at how the two distributions, the likelihood of seeing a lot of these days is changing. And the answer is it is changing. It was getting worse. You can see, so the black curve is past climate, the red curve is around today's climate, and you're seeing a robust shift towards more days with these two weather system setups. And again, roughly about a doubling increase in the likelihood of seeing 2013 levels of the number of days that we saw these two types of weather systems. So we looked at the 2013 event from 3 different angles, 3 different ways of characterizing the event. And if you compare the climate centered around 2013 with the late 1800s, roughly the degree of global warming, we got a pretty consistent answer across the board, with saying it was about twice as likely that that event happened due to climate change. I think I've got about 5 minutes left. So there you go. There's your answer. That's 2013. There's quite a lot of specific work that you have to do to get those sorts of answers for an individual event. We haven't, I don't think any subsequent work has been done in that area. That is a gap in the research field, in my opinion. What are the other known unknowns moving forward? First of all, is when I said that the reason for this, the patterns of the red in that first figure were due to 2 things. One was ozone hole, ozone depletion over Antarctica, and 2 was greenhouse gas emissions. Question going forward into the future is, how is the recovering ozone hole going to interact with future carbon emissions going up? How do they combine to actually change drought risk going forward? That's quite an uncertain question right now, and a lot more modeling work needs to go into that, because it's really hard to model that ozone recovery properly in the climate system. But the second one that I really want to hammer home in the last couple of minutes is, this is a point that I don't think many people have really thought about, is when we said $1.5 billion for the 2013 drought, when is it that these impacts of drought, which are slowly worsening, I say slowly in a relative context, about doubling in likelihood of these things happening for every degree of warming, when are those impacts actually the rapidly warming impacts to do with heat, which happens to be occurring at the same time as a drought? This is what we call compound extreme events. And no one's looking at this right now. We just write off heat in New Zealand and dismiss it, think it's not an issue. This is a paper from 14 years ago, Bryant, 2007. This has been done elsewhere in the world. It's shown comprehensively that you can have levels of heat stress in cool climates like New Zealand. It affects humans. But I really wanted to just hammer home, this is to do with heat stress in dairy cows. So this is A and B. This is one breed, I can't see because of I think Holstein Friesian, and then Holstein Friesian New Zealand Jersey Cross. I think that makes up about 80% of New Zealand's dairy industry herd across country. Here's this rule of thumb. THI is basically an index of heat stress. When you have THI above 70, this is New Zealand, using New Zealand data and milk yields from New Zealand data from this 2007 paper. The authors found that basically once your THI got above 70, you started to see declines in milk yield. What is happening right now? Well, I ran these numbers about 2 days ago. No one is really looking at this, and I'm quite concerned by it. But basically, you're seeing over the last sort of, this is so 17, 18, 18, 19, 19, 20, 2021. These are the sorts of numbers that you're seeing in Northland, Waikato, and Canterbury right now. Waikato is a place for which you're seeing over 8 weeks with THI above 75, which is comprehensively where milk yields are starting to decline. And that is due to physiological heat stress in the animals. What is going to happen if temperatures continue to climb? We don't know, we're not looking at it. This is some preliminary work I did last year. This is looking at the increase in the number of hot days defined on a relative basis and a local basis. When you're comparing the most recent decade, the 2010s, versus the 1980s, and saying that's a proxy for roughly half a degree of global warming. And you're seeing these really, really robust shifts on either side of the summer. So you're actually seeing these big red blobs here, where it's approaching more than a 5-fold increase in hot days since the 1980s. These are signs that there are actually some sort of soil moisture feedbacks going on that are going to actually further intensify temperature extremes relative to the mean changes in temperature. We're not looking at any of this either. And the main reason why I want to really stress this is because it's fine if the rate of change of temperature extremes and the rate of change of drought go up at the same pace of global warming. That's sweet. Then whether the impacts associated with the drought year are to do with the heat or the aridity doesn't really matter, but that's not the case. Drought is going up at a fast rate relative to drought in other parts of the world in New Zealand, but by far and away, temperature extremes and high temperature extremes increase by an order of magnitude more rapidly than hydrological extremes. And so if we are failing to realize what impacts within a drought event are due to the heat, direct heat, and which are due to the drought itself, then suddenly we might be some hidden impacts in here which are going to get a heck of a lot worse really, really fast without us realizing, and we're going to underestimate future impacts. So that's something I kind of just want to leave on, that this is something that we haven't thought about. It's not really being researched anywhere. It's not being funded anywhere. So it's something that's worth people to think about. Cheers.
Kia ora, Luke. Thank you very much. That was a quick presentation. Thank you. We just wanted to draw your attention. There's some chat going on in the chat panel. Anita Reeford at Lincoln University has a current Deep South Challenge project looking at primary sector preparedness under climate change, and an aspect of that research will include heat stress in dairy cows. So perhaps that can be an offline conversation. And also to say that in next week's webinar, we'll have Kenny Bell from Manaki Whenua, who has looked at the impacts of soil moisture on productivity in dairy cows. So there's related work going on, and it's a perfect example of how we want to tie these conversations together over the next month. So Luke, hopefully you'll be able to keep joining us over the next 2 webinars, and also come to the, not to put you on the spot or anything, come to our symposium as well. But for now, can I ask Sue you to unmute yourself, Sue, and to share your screen and introduce yourself as well. Thank you, Sue. Suzanne Rosier from NIWA. Great, Sue.
Okay, thank you very much. Alex, can you hear me and see my
Yes,
first slide?
everything's perfect.
Okay, thanks. Yes, thank you very much indeed. I'm going to try and be extremely quick. Andrew and Luke have essentially done the hard work and told you about drought in New Zealand. I'm really just taking a short spot to really tell you more about some potential work that can be done on drought here in New Zealand, using a slightly different sort of modelling stream, if you like. So I'm trying to just give a little overview of climate modelling in general, and give you a bit of a feel for the fact that essentially we use, you can think of essentially having a toolbox where you might use a different tool for a different job. And in terms of climate modelling, there's a huge range of complexity in those models, and there's always a trade-off between the detail in which we can model and the spatial detail we can get, and then the confidence we can have in by running models lots of times. So what I'm really just trying to show here is that there's a bit of a spectrum, and hopefully, I think you can see my cursor. I'm trying to pick out this in the left corner here. I'm just trying to illustrate this, one of the most very complex types of climate models that we use, where we fully resolve and model the atmosphere and the ocean and all the land surface processes. These Earth system type models are incredibly brilliant, incredibly complex, but also computationally very, very expensive. So we can only afford to run them a few times. That's fine for many aspects, but if you are interested in things like climate extremes and weather extremes, where by definition the events you're trying to get at are very rare, then these really complex models are of somewhat limited use. Further along the spectrum, though, we've got slightly simpler models like this one here in the middle, which is an atmosphere where we model the atmosphere only, and we tell it what we think, what we know the sea surface temperature is at the bottom. These sorts of models very much in use. We can run those maybe a few tens of times up to 100 times. I want to tell you about a project called Weather at Home, which is based in Oxford and runs a region for Australia and New Zealand, where in this case here, we've got a regional model embedded in the global model, whereby we can model the region in more detail. The thing about Weather at Home is that it gets its computing power from volunteers all around the world. And that's a big deal, because it means that we can then run these models thousands of times, and that lends itself extremely well to when we want to learn about the processes affecting weather and climate extremes, because for instance, if we've run our model thousands of times, then we have a lot more confidence in what, say, the 1 in 1,000 year event might be. So for something like drought, which is at the extreme end of the distribution, if you like, that can be very, very useful. So this is what New Zealand looks like in the Weather at Home model. The size of each grid square is 50 kilometers square. So if you're interested in exactly really what's happening very much in your backyard, then it's not going to give you information on that scale. This is nothing like as fine scale as the sort of things that Andrew showed. But the trade-off is that you can have more confidence in the very tails of the distribution. So this is so at each one of these grid squares, we've got these thousands of runs that enable us to look at the distribution of how things like temperature and precipitation are changing, what they are and how they're changing. But in particular, right out here in what we call the tail of the distribution, where we're looking at extremes that don't come along very often. This stream of modelling is very useful for that, and we can say probabilistically about how we think the likelihood of these sorts of events is changing. What we've done here in New Zealand is to run some projections of these, so going out to the 2090s under a project called HAPPY, which is 0.5 degree additional warming prognosis and projected impacts. This is temperature up the side, time across the bottom. By the end of the century, we're looking at temperatures that are reaching about 1.5 and 2 degrees, those particularly because of the Paris Agreement. So there's great interest in seeing how the climate, and in particular the extremes, might be changing under futures 1.5 and 2 degrees warmer than pre-industrial. And here on the left, the orange and yellow colours, this is the pattern of sea surface temperature warming that's been added to the current decade to get those 1.5 and 2 C scenarios. So we've put those projected sea surface temperature changes underneath the Weather at Home model, and we've run them through to the 2090s. And supported by the Deep South, we have also created a +3 degrees future as well. So we've got those there, potentially can be used to tell us now something about changing extremes and drought conditions. I think I've got to wrap up very quickly, but just to let you know, a study led by Frame et al. That was published last year, that was originally done in conjunction with the Treasury, we use this sort of probabilistic information from these very large sets of model runs to look at the changing likelihood of extreme weather. And we combined those with the financial losses to try and estimate what the human influence on climate is costing us in terms of damaging weather events. And essentially so we were looking really, what is the price tag of the human influence on climate as it's playing out through weather extremes. Luke mentioned about the droughts costing on the order of 1.5 billion to the economy, and we combined that with an estimate of what fraction of the change in these events is due to human influence, to have a very first stab at this price tag of how much climate change, human-induced climate change, is actually costing us in terms of the insured losses in flooding and economic costs when it comes to drought. So very, very quickly, other studies of drought to date using weather at home. Pete Huey looked at drought in Kenya. David Rupp looked at drought in the Western US. They both found that circulation changes such as associated with El Nino were important. And also it highlights how it's actually quite hard to define drought, and depending on how you define it, you're likely to get different answers. And that's the sort of work that we're also doing under the Whakahura MB Endeavour project. We're looking at the ways that these might play out, and in terms of the impacts. And as Luke mentioned, even if there's no this study by Pete Huey found that actually even they couldn't detect any change in precipitation, but they could detect a change in temperature, and that will affect, for instance, the demand for water. So then you need to couple to the relevant other models to assess those impacts properly. So that's the sort of work that we're also looking at under the Whakahura project. And I think that's probably easy enough for me. Thank you very much for lending me an ear, and feel free to get in touch at my email address there.
Kia ora, Sue. Thank you so much. And yep, great. Sorry, everyone, we have a very limited amount of time for questions. So we're just going to go to some sort of high level and I suppose questions that really get to the nub of the matter. And our first question is going to be from Terry Moore, who asks about research. And this is a question for, if Andrew and Luke, you could both record, yep, thank you. Any of you can volunteer to answer this question. Talking about research into the economic impacts of heat and drought areas, and then looking towards a future in which, is it conceivable that farms in the worst affected areas could actually be abandoned? Would anyone like to take that question? Andrew, perhaps?
Yeah, just to say that that type of research is absolutely important and critical, and we are working along those lines, developing our research plans to be much more around impacts and implications of climate change, not just about the projected changes in the physical system. So this is an important area of research that we are moving into, and the work that's been presented by Luke and Sue has already established that we are working in this space already, in fact. What happens in terms of farms in those areas is going to be something we have to see how that progresses. I mean, adaptation is all about how we can change our systems to adapt to those changing climates and other pressures. Potentially one outcome will be that current management of farming, the way that we do at the moment, is no longer appropriate under those types of climates. But that is all about how we adapt. And the one thing that we've got on our side is that climate change is happening relatively slowly. We've got years to continually adapt with the way that we do things to adjust to these changing climate parameters that we're forecasting.
Thank you, Andrew. I'm going to throw this question to Sue, actually, even though it was asked of Andrew. It's a question about, which is something we hear a lot about, the uncertainty of climate modelling, the inherent uncertainty of climate modelling, and also the, I'm going to put it in quotation marks, extreme low likelihood of the RCP 8.5 scenario. So can you talk about, and it's in relation to a presentation by Willem de Lang, I think to say his name. Can you talk about your response to this question of the utility of climate modelling and whether we should be using RCP 8.5? Just unmute yourself, Sue, thanks.
I'm not quite sure what the main question is, but I'm given to believe that RCP 8.5 still represents a pretty high emission scenario that we are probably unlikely to follow in practice. That's my rather limited understanding. I think, I mean, nobody knows how the future is going to play out, of course. But I do think perhaps it's helpful to consider a more of a mid-range scenario when you, if you want to, if you want to feel a little bit more confident. My understanding is that the path we're on at the moment, or certainly how we would hope to include technological changes that will reduce emissions in future, I believe that 8.5 still represents a scenario that's hopefully very much towards the top end of the very worst, and hopefully not that realistic. Looks like Luke wants to jump in, and that's probably a good thing.
Yeah, I just wanted to add one further comment, is that, I mean, there was a comment piece recently in Nature that has shown that this RCP 8.5 is 100% not a business as usual scenario. It is an acceleration relative to today. If you compare the potential changes that you have to do in coal output and all these things, population changes, is just not realistic. A more realistic business as usual, if you're using the old framework, would be RCP 6.0, perhaps. I think what I would say, though, is that in light of SR 1.5, the 1.5 and 2 degree framing of the Paris Agreement, there has been quite a robust shift in the research community to push towards looking at changes associated with increments of warming. So what is the changes associated with 3 degrees of warming, 2 degrees of warming, 1.5 degrees of warming? And that actually sort of bypasses the questions of whether these scenarios are actually realistic or not. But to the question of whether RCP 8.5 is a realistic, fair representation of business as usual, I would say 100% not.
Kia ora, Luke. We have so many interesting questions in the chat panel, and we've just run out of time, but we hand on heart promise to go back to all of our presenters and invite them to respond in writing to every question that's been asked. And just to reiterate, at the end of the 4 events that make up this Rolling Symposium, we'll put a package together about with all of the slides, if the researchers are willing to share them, with the questions and answers, and with some evaluation from the whole event. So thank you so much to our 3 presenters today, and for keeping yourselves to time. It's not easy. And thank you, and massive thank you to everyone who's joined us online as well. We invite you to register early for the symposium and to make sure you come to our next 2 webinars to contribute to the conversation, because clearly you all have some really valuable experiences, knowledges and arguments to further. So thank you very much, and we really look forward to seeing you next Tuesday at 11 AM. Ngā mihi nui kia koutou katoa.